is how far the sample average is from the hypothesized average measured in standard deviations. So the t statistic is equal to the sample mean 570.88 minus 529, and then divide that by the standard error of 42.56, and this comes up to show this t statistic is 0.984, which means that the sample average is 0.984 standard errors above the hypothesized value. Now we need to find if that is high enough to go into one of the tails, either the positive or the negative. Here it's positive, so we're going to be looking at the positive tail. And we can do this two ways. The first is we can look at 0.984 compared to the critical regions. So critical region here, 0.984, which is just about at 1, is not in the critical region. So we would fail to reject. Another way to look at it is to look at where 0.984 is really in the standard normal distribution. And this becomes t dot dist 0.984 with 7 degrees of freedom, and we want it to be cumulative. So we need to go to Excel and this becomes equals t dot dist 0.984, 7 degrees of freedom, and we want it to be cumulative. So 0.984 is at the 82% mark in the standard normal distribution, so that there is 82% of the distribution to the left, which leaves 0.18 to the right. The 0.18 is called the p-value. It's where it really is in that tail. And the 0.18 is much greater than 0.025, so that we are not in the rejection region. If we were in the rejection region, this p-value would have to be less than 0.025, would put it somewhere up in there. Because it's a two-tailed test, we have 0.18 on the upper end. We also have to include the lower end, so that the p-value for this test is equal to 2 times 0.18, so that 0.36 is the actual p-value. We need this 0.36 because we can compare it to the 0.05 two-tailed significance level. Null hypothesis is not rejected. We have failed to reject the null hypothesis. And if we look at it from the p-value, the p-value is 0.36, which is much greater than 0.05, which means we're not in either tail. Or looking at it from the 0.984, we aren't at the 0.236 that would be required to reject the null hypothesis. In this particular example, we fail to reject at the 0.05 level, and we can report that. But also, if someone asks how close were we to rejection, we compare the 0.36 to the 0.05. We're nowhere near the rejection region. So that for this one, we would fail to reject the null hypothesis that the actual average is 529. These are hypothesis test examples. And you need to write down what the null hypothesis is, what the alternative hypothesis is, where the rejection region, where the critical region is. To test for significance, what's the t-value, etc. Okay, so the first one, the mean score is 516. A test prep company wants to say that they can raise that score. What's the null hypothesis? If this company wants you to take this class, what's the null hypothesis? Actually, it's easier to do. What's the alternative hypothesis? What does the company want to prove? That the test result will be higher. So the null hypothesis is that there is no change. The null hypothesis, there is no change. The alternative hypothesis is what they want to prove. So where's the rejection region? Which way does the alternative point? If the alternative is an arrow, where does it point? So the rejection region is on the right. What would the significance level be? The alpha level, the chance of making an error, what would it be for you if you were going to pay them to take a test or to take the test prep class? Would you rather be sure that they knew what they were doing, or is it okay if they're kind of sure? This is the only decisions that the statisticians can't make. They're going to charge you $500 or $1,000 to do this. How sure do you want to be that it works? You want to be pretty sure. Your alpha level, the chance of rejecting the null hypothesis when it's wrong, basically your chance of taking this test and not getting anything out of it. If you fail to reject the null hypothesis, you would want a significance level that was very small, like 0.01. What does the company want for their significance level? They want to be able to say, yes, our company test works. Their alpha level is going to be bigger. They're going to be at 0.05 or even 0.1. You want to be out here. They want their rejection region to start here. So that a hypothesis test is a tug of war between who's doing what to whom. A drug company wants to introduce a new drug. What alpha level do they want? Versus what alpha level do I want if I'm going to take their drug? They want to be able to say that it works. They want to be able to reject the null hypothesis, that there is no effect. I want to be sure that this thing doesn't kill me. So there's always two sides to a hypothesis test. What is the conclusion if the null hypothesis is rejected? If I reject the null hypothesis, I can only do two things: reject and fail to reject the null hypothesis. If I reject the null hypothesis, what am I saying? It works. If I fail to reject, I'm saying it doesn't work. All right, here's the second one. Mean body temperature is 98.6. A doctor suspects this number is incorrect. What's the alternative and the null hypothesis? Look at the wording. What does it say? A doctor suspects this number is incorrect. Does it have a direction? For this one, The null hypothesis is that it is 98.6 versus the alternative that it's not 98.6. Where's the rejection region? What result will cause me to say it's not 98.6? What would I have to get out of a test? I do a test of 15 people. And then 98.6 really isn't very good. Some people have a higher body temperature. Some people have a lower body temperature. There's a range. So if I get the temperature of 50 people, what would the average have to be for me to say it's not 98.6? Like 102? Or what? 92. The rejection region is on both ends. The alternative points to both ends. Basically, it says not in the middle. What kind of alpha level do I want for this? What's the significance level for this test? What does this doctor have to prove? Pardon? Exactly. All of science is wrong, which is a good way to put it. So what would the alpha level have to be for this guy to pull it off? It would have to be like 0.01, 0.001. He's got to prove basically that all of science is wrong. So he's got to be way out in the end. This is like saying aliens came to my house last night. E.T. showed up. What do I have to do to prove that E.T. showed up? Can I just go out and say, hey, E.T. showed up. I got a picture. Extraordinary claims require extraordinary evidence. So I better be able to produce E.T. Then people would believe me. Sort of. All of that goes into what's the significance level going to be. The third one, we're going to do this, and if you go into My Open Math, I believe the file is hypothesis test data. And there's the numbers. We're still on number 3. Researchers examined 150 similar hypothesis tests on blood pressure. All of these tests were conducted at the 0.05 level. What's the chance that I got 4 results that were wrong? I rejected the null hypothesis in 4 of these experiments. What's the chance that any one experiment was a mistake? That's the 5%. If I did 150, how many would I expect, purely by chance, to come out wrong, to reject incorrectly, to say that the null hypothesis is not true? I have rejected it when it really was true. For each one, there's a 5% chance that I made a mistake. Officially, 5% of my 150 I would expect to be wrong purely by accident. This is another implication of that chance of error. So I would expect more than 4 to come out incorrect. If I did 100, I would expect 5. And this is something that there's a big argument about in statistics all the time, because they do more and more looking at accumulated results. It's called a meta-analysis. So if somebody goes out and he gets every experiment that they can find on a particular thing, and they look at what the results of all of these tests were, so that if they are conducting multiple tests or looking at multiple tests, they have to decide whether they think that 4 out of 150 is really wrong. How many would they expect? What's 5% of 150? 7.5. I would expect 7 or 8 of these things to be wrong. 4 is actually on the low end. When they do a medical experiment, they have a stack of things. There's a whole bunch, sometimes as many as 20 individual tests in their experiment. And they have to decide, if they're using a 0.05 alpha level, whether 5% of those are wrong just because. We used to have arguments about this in meetings because I think that that's silly. Any one test stands by itself. It's got a 5% chance of error. If you've got 20 of them and then claim that 4 of them are wrong at the 0.05 level just because, takes an accumulation of information that you are not justified in making. You got one experiment, you do one thing. You got one result. When you go to the next one, it's independent of the one that came before. All right, so there are people on my side, and then there are the people on the other side that said for repeated experiments, 5% are going to come out incorrectly. And you have to discount any results along that line. Now, number 4, graduate admission tests, and this is where that data comes in. The test administrators say that the average is 529. 8 people took the test. What are the null and alternative hypotheses? If I'm looking at their data, I get 8 people. Can I say the average is 529? What's the null hypothesis? What's the status quo? There is no change? That's the null hypothesis. The null hypothesis is that the average score is 529. What's the alternative hypothesis? That it's not 529. This is not always clear. Sometimes you've got to fight with the wording on this. Where are the rejection regions? Where does the alternate hypothesis point? Any place but the middle. So if I do a test and the result comes out to be high or low, but different than 529, then I say I have rejected the null hypothesis. All right, now we're going to conduct this one. You've got to do this one. We got the data in that file. And this is on MyOpenMath hypothesis test data. Yeah, hypothesis test data there. And all we're going to do is get the mean, the standard deviation, the standard error. We're going to go through the procedure here. So for this data, it's number 4, we need the average. And you can do equals average and mark the data, or go to the automatic command. That's that little sigma up there at the top. And your screen may show it differently depending on the resolution. But I'll do it the easy way. I'm going to get the average. And the average is 570.875. The next thing I need is the standard deviation. And for these, it's always STDEV dot S. I want the sample standard deviation. This uses the divisor of n minus 1 instead of n. Mark the data. And the standard error is 120. The next thing I need is the standard error of the mean. For any statistic, it doesn't matter, confidence intervals, hypothesis test, general analysis, you always get the average, the standard deviation, and the standard error of the mean. That tells you what the layout is. What's the formula for the standard error of the mean? Standard deviation divided by the square root of the sample size. Sample size is 8. 1, 2, 3, 4, 5, 6, 7, 8 equals standard deviation divided by square root SQRT of 8. And the standard error of the mean is 42.55. Now we've got two things we need to do. One is to find out what the cutoffs are for the critical region, and two, how far are we from our hypothesized value with that average? Does the sample evidence suggest the average score is different than 529? We have an upper-lower critical region. The average is in the middle. The average is 570 point, what was it, 88? 88, that's close enough. The standard deviation is 120.37. The standard error of the mean, 120.37 divided by the square root of 8 is 42.56. You can use more or you can use less decimals. Basically, if the result is going to be different, if you're using 2 versus 3 decimals, you're in the wrong place. Things are too close to call. So 2 decimals is more than enough. What are the cutoff values for my critical regions? What do I need to get the critical region cutoff points? I need a critical region size. I'm going to use alpha equals 0.05, just because this is a two-tailed test. How much is going to be in each tail? Half of the 0.05? This is always the way it goes. If it's a two-tailed test, you split the probability between the two ends. 0.025 here and 0.025 here. I need to look up the t-value that cuts off 2.5% on the low end and the high end. And for that we need Excel. pick a spot. This is the command, equals t dot inv. We want to go from a probability to a value. The probability is 0.025, half of 0.05. And then we have, for the t value, degrees of freedom. Sample size is 8. What's the degrees of freedom? N minus 1, 7. And that's all it needs. And I get minus 2.36. Then this is minus 2.36. There's 0. The value of t of minus 2.36 cuts off 2.5% on the low end. What about the upper end? What's the value on the upper end that cuts off 2.5%? Two ways to do it. What's the easy way? Normal distribution, the t-distribution, are symmetric by definition. So what would the upper end be? 2.36. Or, if I go back to Excel, I'm going to repeat this t command, equals t.inv. What probability would I give it to get the upper end? And remember, it always comes from the left, from the low end up. 0.975, 97.5. 0.975, 7 degrees of freedom. And I get exactly the same number, except it's plus. This is the good thing about t distribution and z distributions. They're symmetric. So my cutoff criteria for this test is, does my result fall more than 2.36 standard errors above or below my hypothesized average? So my average is 570, 571 basically. How many standard errors above or below the hypothesized value is that? Is how far the sample average is from the hypothesized average measured in standard deviations. So the t statistic is equal to the sample mean 570.88 minus 529, and then divide by the standard error of 42.56, and this comes up to show this t statistic is 0.984, which means that the sample average is 0.984 standard errors above the hypothesized value. Now we need to find if that is high enough to go into one of the tails, either the positive or the negative. Here it's positive, so we're going to be looking at the positive tail. And we can do this two ways. The first is we can look at 0.984 compared to the critical regions. So critical region here, 0.984, which is just about at 1, is not in the critical region. So we would fail to reject. Another way to look at it is to look at where 0.984 is really in the standard normal distribution. And this becomes t dot dist 0.984 with 7 degrees of freedom, and we want it to be cumulative. So we need to go to Excel and this becomes equals T dot dist 0.984, 7 degrees of freedom, and we want it to be cumulative. So 0.984 is at the 82% mark in the standard normal distribution, so that there is 82% of the distribution to the left, which leaves 0.18 to the right. The 0.18 is called the p-value. It's where it really is in that tail. And the 0.18 is much greater than 0.025, so that we are not in the rejection region. If we were in the rejection region, this p-value would have to be less than 0.025, would put it somewhere up in there. Because it's a two-tailed test, we have 0.18 on the upper end. We also have to include the lower end, so that the p-value for this test is equal to 2 times 0.18, so that 0.36 is the actual p-value. We need this 0.36 because we can compare it to the 0.05 two-tailed significance level. Null hypothesis is not rejected. We have failed to reject the null hypothesis. And if we look at it from the p-value, the p-value is 0.36, which is much greater than 0.05, which means we're not in either tail. Or looking at it from the 0.984, we aren't at the 0.236 that would be required to reject the null hypothesis. In this particular example, we fail to reject at the 0.05 level, and we can report that. But also, if someone asks how close were we to rejection, we compare the 0.36 to the 0.05. We're nowhere near the rejection region. So that for this one, we would fail to reject the null hypothesis that the actual average is 529.